going to tell us about online algorithm for spectral hypergraph sparsification.
Okay, is this working? Okay. Yeah, thanks. So I'm going to talk about online algorithms for spectral hypergraph sparsification. And this is joint work with Chuen, Tung. Basically, I call him Alex. And Tasuku Soma. Yeah, and the slides are mostly by Soma, but mistakes mostly by me. Okay, let's go. Okay, let's start with very basic stuff. So what is spectral sparsification for? Not hypergraphs, but graphs. And well, to explain it, I need to introduce graph Laplacian, which is main object in spectral graph theory. So let G be a graph that might be weighted. So we have weights on edges. And the graph Laplacian matrix is defined as this, this way, but okay, you don't need to understand this definition. What's important here is its quadratic form. So quadratic form of Laplacian is basically given x, we get x transpose LGX, and it turns out that it is equal to the sum of the weight of the edge times xi minus xj squared. And we take the sum over edges in the graph. And how can we interpret this quadratic form? There's nice interpretation here. So let's look at undirected graph. Weighted, it might be weighted as an electrical circuit. So each edge is resistance. So weight is corresponding to the resistance. And okay, if you feed vector x, we are basically setting potential of nodes. And then, okay, the potential difference may cause you electrical current. Then what will be the basically power of the circuit incurred by that current? That is given by the quadratic form. For some, well, I guess physically speaking, it should be called power, but for some reason, this is called energy in the literature. Anyway, okay. So quadratic form is nice also in combinatorically because it captures it. Yeah, it is like generalization cut function. So if you feed given like vertex subset x, if you feed characteristic vector of x to the quadratic form, what you get is basically the cut weight of x. So here we have x, and yeah, you can see from the definition of quadratic form that if an edge is cut, x or xj is 1, and the other one is 0, so you get 1 here. So basically, we sum up all the weights of edges cut by x, which is nice. Okay. And what is spectral sparsification for graphs? Not hypergraphs yet. Yeah, we want to reduce the number of edges from the graph. Well, that's basically good, right? Because we don't. Okay, so in general, we may have n squared many edges, but if you can reduce the number of edges, then okay, it doesn't like take up much memory. Or also another advantage of doing is that well, there are many algorithms that whose running time depends on the number of edges, but if you can reduce the number of edges, then we automatically get speed up. So we want to sparsify it. But okay, of course, we need to preserve something, preserve some property of the graph. And okay, the definition used here is the following. A weighted subgraph G tilde, which is, yeah, weighted subgraph is called epsilon spectral sparsifier, where epsilon is a parameter. If it preserves the quadratic form up to 1 plus minus epsilon factor for any x. Yeah. So given a dense graph, we want to sparsify preserving quadratic form. Yeah, spectral sparsifier, well, okay, from the observation I mentioned, if you have spectral sparsifier, it preserves all cut values, so you can automatically speed up any like cut-related algorithms, which is nice. And well, there are many works on spectral graph sparsification, and the best known upper bound is n by epsilon squared. So we don't need polylogarithmic factor here, just n by epsilon squared. And this is basically, okay, in a sense, it is tight because just to preserve connectivity of the graph, you need n many edges. So you cannot like go below n. And okay, dependence on epsilon squared is a little bit tricky. Well, okay, we have some sketching lower bound, but I don't want to go into the detail here because it's not so relevant now. Okay, so let me go to hypergraph. Yeah, Yeah, so what was hypergraph? Okay. Yeah, I guess everyone knows about hypergraph, but okay. We are given a hypergraph with that might be, yeah, okay, edges might be weighted. And what was hypergraph cut function? So if you have vertex set x, it just counts it or just computes the total weight of edges that are cut by x. And when we say a hyperedge is cut if x has non-trivial intersection with the hyperedge, which means, okay, it must include at least one vertex, but not all vertices in the hyperedge. Then we call it is cut, and we just count the total number of total weight of edges cut. Okay, so natural question here is that we have a very nice spectral sparsifier for graphs. Can we design sparsifier for hypergraphs? One issue here is that hypergraph cut function is not a quadratic form in the usual sense. Yeah, so graph cut function can be written as a quadratic form of a matrix. So we can do some linear algebra there. But here it is not a quadratic form of a matrix. So that causes a lot of issue. But we can think about, well, quadratic form like function like that. So here we take, so this is quadratic form for hypergraph H. And this is like sum over edges of weight times, okay, max xi minus xj squared. What is it? So we take maximum over nodes in the, I guess I have laser here. Okay. Yeah, we take maximum over ij, nodes ij in E. So if you feed characteristic vector of vertex set x, then if it has non-trivial intersection with edge E, then this part becomes 1. Well, if all the nodes in the hyperedge are contained in X, then all of them become like 1. So this part becomes 0. And none of them are contained in X, then this all xi, xj becomes 0. So this part becomes 0. So it doesn't contribute to the quadratic form. So this counts, or this computes the total weight of hyperedges cut by X. Yeah. Okay, nice. So yeah, we can define spectral sparsifier for hypergraphs using this quadratic form-like function. A weighted subhypergraph H tilde is called epsilon spectral sparsifier of H if it preserves quadratic form up to 1 plus minus epsilon factor for every x. Yeah, that's easy, right? So okay. By the way, this notion was introduced by me, which is nice. Okay, so what's known about hypergraph sparsification? So yeah, Kogan and CrossGamer introduced the concept of cut sparsifier for hypergraphs. Well, okay, there's some previous work that implicitly showed existence of cut sparsifier, but the concept itself was introduced here. And at the time, the bound was n times r, basically. And here, n is the number of vertices, and r is the maximum size of a hyperedge. Yeah. And well, spectral version was introduced by me, and at that time, bound was n cubed. Oh, okay. So maybe you have a question like, why do we want to like preserve quadratic form for hypergraphs and not just for cut functions? But yeah, okay. Maybe I don't know. For like in machine learning or data mining context, people have studied this quadratic form a lot. Well, before like, well, they don't like explicitly call it quadratic form and they try to preserve it, something like that. But they implicitly use this function a lot to capture like higher order relation between, I don't know, nodes or whatever in semi-supervised learning or link prediction or other application in machine learning, data mining. So it is natural to try to preserve it using small number of edges. And yeah, people have tried to actually manage to improve the bound here all the way down to basically n log r. So yeah, this is like great because in general, hypergraph can have exponentially many hyperedges, right? It can have 2 to the n many hyperedges, but to preserve the value of quadratic form, you only need many hyperedges. So that's right, compression, right? So that's what's known. Okay, so well, this is very nice result, but there's some drawbacks because okay, your output is gonna be of size n, well, weighted hypergraph of many hyperedges basically, but the input size can be exponential. So, and if you look at algorithm, those previous algorithms, basically you need to keep the entire hypergraph in the memory. So your final output is going to be very small, but the working memory would be very high. That's not nice, right? So a natural question here is that whether we can construct spectral sparsifier of a hypergraph using like only polynomial space. So that's the main motivation of this work. Okay. So let's see the problem setting. Here, hyperedges and voids arrive in stream. And okay, from E1, W1 to EM, WM, M is the number of hyperedges. So it can be exponential in N. And when the ith edge void pair arrives, well, actually, this is not just streaming. I'm talking about online settings. So we irrevocably decide whether to include EI to H tilde along with its weight. H tilde is going to be the final output, final sparsifier we are going to output. And okay, and we just have polynomial poly in N working space. Okay, the question is whether we can do this. For some technical reason, it is convenient to introduce relaxed notion of spectral sparsifier, which allows for additive error. Weighted subgraph H tilde is called epsilon delta spectral sparsifier if it preserves quadratic form with multiplicative error of 1 plus minus epsilon and the additive error of delta times the L2 square norm of X. Okay, so what we showed. We showed there is an online algorithm that outputs hypergraph spectral sparsifier, and the boundary is like this. So there's an online algorithm that outputs epsilon delta spectral sparsifier with that many hyperedges. Okay, I'll try to interpret it later. But anyway, the size of space is n squared, which is very small compared to the exponential. And here, the boundary is basically, okay, you can ignore these log n log r, but basically n times log w. And w is the total weight of edges, hyperedges. And this part can, oh, yeah, sure.
Wait, so is that n squared bits or like n squared words? And if it's words, what's the word size? Because
basically, we keep weighted graphs, so n squared words.
Okay, and each word will have like log weight.
Yeah, maybe, yeah. Oh, you care about it?
This expression, if you have that many hyperedges, it's already more than n squared bits of.
Oh, yeah. So the output size might be, okay. Yeah, so this is a working space, and this is output size. So yeah, this can be bigger than n squared, yeah. Right. Yeah, so for general hypergraphs, W can be like 2 to the n. Okay, let's say for general unweighted hypergraph, W can be 2 to the n. So we may have like extra n factor from here. But anyway, this is like, okay, so this is not as small as the smallest spectral sparsifier for hypergraphs we know, but we can construct it in online fashion. Yes. And okay, so this is some kind of specialization. So if the input stream consists of like, unweighted R uniform hypergraphs, then we get this bond. So you can ignore log part. Then, but basically, n are many hyperedges. We know that we can do it with n many hyperedges, but so we have extra factor of R. But yeah, that's what we got. Okay, so let's go into the detail of algorithms. Oh, okay, I spent 15 minutes. That's good. Yeah, so this is a general framework of constructing spectral sparsifier, well, okay, even for graphs. For each edge, we compute some sampling probability P, and then what we do is the following. For each hyperedge, we add a copy of edge E to the sparsifier with weight WE divided by P with probability P. So this is the general framework. I don't specify P at all yet, but we already have some properties. If you look at the expected value of the quadratic form of sparsifier, it is equal to the original quadratic form value. So it's unbiased. And the expected total number of hyperedges is sum of P. So we want to like make it small. Yeah, we usually weight is bounded by polynomial in N. So yeah, let's do not care about let's not care about the like bit complexity of weights. Okay, so how should we choose PE? So that's the challenging part. To get sparse sparsifier, we want to basically choose small PEs, but that causes you a high variance of cut function. So yeah, but if you on the other hand, if you have large PEs, then of course the graph sparsifier becomes dense, which is not good, but the variance becomes small, so we can easily like show that it is a sparsifier. So we need to carefully choose PE. So for example, in the graph case, if you have a bridge which has cut value of 1, you need to always keep it to preserve the cut value because there is a cut of value size 1 crossing that edge, so you always need to keep it. But on the other hand, if there is a like complete graph-like component in the graph, then all the cuts crossing that complete graph-like component has high cut value. So you don't need to keep all the edges in the creek. Basically, you can always get sparsifier with many edges there. So we need to carefully choose sampling probability. Okay. Yeah. So okay. For the graph case, we can use a parameter or value called effective resistance. But for hypergraphs, we need some careful analysis or idea. What's popularly used in the context of hypergraph sparsifier is reweighting. Given a hypergraph, we first construct creek expansion. So for each hyperedge, we replace it with a creek. And okay, so here is the picture. So if you have 2 hyperedges there, we replace them with creek. So so this pair is shared by 2 hyperedges, then basically we have 2 edges there. Yeah, we want to do it because we are assigning weights to those edges. And there's nice lemma. We can, okay, so this is a little bit complicated thing. So what we want to do is assigning weights to edges here. And how do we do it? So first we have edge for each hyperedge. And basically we distribute the weight of hyperedge to edges in the creek corresponding to the hyperedge. So this is the first condition. So CEUB is the weight for the pair UB given by hyperedge E. So basically, we are distributing the weight of hyperedge to edges in the creek. And this is very complicated thing. So if a pair gets positive weight, then its effective resistance, well, okay, you don't need to understand what the effective resistance is, but it's a very important parameter in spectral graph theory. And that effective resistance must be equal to the maximum effective resistance in the creek. So yeah, it's not trivial at all whether we can find such like weight assignment to edges in the creek expansion, but actually we can do it. And it might be kind of mysterious, but okay, did we mention it? No, okay. So if you use those weights to, yeah, so if you get those weights, and if you assign sampling probability P, if you set P to be weight of that edge times the effective resistance of an edge in the creek corresponding to the hyperedge, you get a spectral sparsifier.
Effective resistances are functions of the weights on edges?
Yep. Yes. And yeah, so magically this works. And you get, it is known that we can get a spectral sparsifier of size basically n. Right. So what we have in the next slide, I don't know. Okay. Yeah. So how can we compute it? So that's the question. Yeah, we know that this weight assignment works to construct spectral sparsifier. So the question is how we can compute it. And actually, we are. I'm going to use it to design online algorithms. So I want to say some words for it. So we can compute the CEUB using this optimization problem. So here, so this is the condition that we distribute weight for WE to edges in the creek. And this is what, J is all one matrix, but this is not that important because this is just to make the matrix non-singular. So this is not important. The important thing is here. So basically we are assigning weights to edges. We get undirected ordinary graph. It's going to be weighted. And we are computing, we are maximizing log det of it. And what is the maximization? What is the maximum value of log det? Okay, log det is basically captures the number of spanning trees in the graph. If the graph is unweighted, and if the graph is weighted, log det captures is actually equal to the total weight of spanning trees, where the weight of spanning trees is just the product of edges in the spanning tree. So basically, we are trying to maximize the total weight of spanning trees here. Then, if you look at KKT condition of this program, you will see that the condition here is met. Okay, so this is the program we are going to use in the online setting. And it's already fit. Okay, so yeah, so this is our online algorithm. Okay, so delta epsilon is a given parameter, and then we set eta to be delta by epsilon, and we keep updating Laplacian. So so we start with zero matrix for L. So L here is just a matrix, Laplacian for weighted graph, and we update Li. We update Laplacian by adding quick expansion of hyperedge EI, where EI is the hyperedge you got. And okay, how do you assign weights? We compute this optimization problem. So we fix the Laplacian you have, and then you have, so the variables here is basically CIUB, and you compute those weights, and then add the quick expansion using those weights. And this is a kind of regularizer thing, which we need to make the proof go through. Okay, so this is the idea. So this is the whole algorithm. So this part is basically the same. Start with empty hypergraph sparsifiers, start with zero matrix, and given a hyperedge EI, solve this convex program to get CIUB weights on edges in the quick expansion, and then update it using those weighted quick expansion. And then, okay, now what is the sampling probability for the hyperedge EI? So that's going to be, well, basically similar to the offline case. It's going to be just the WI, which is the weight of the hyperedge EI, times the effective resistance type of thing. Oh, this is another representation of effective resistance. Okay, also it's a kind of bridge. We have regularizer here, but this is basically effective resistance of the resulting weighted quick expansion. Okay, and this is similar to the, this is coming from the framework. So when you add hypergraph edge EI, then the weight should be WI divided by PI to get unbiased sparsifier. So this is the algorithm. Okay, so I want to say, I don't go into the detail of the analysis, but I'm going to say some few words about it. Okay, so good thing of this algorithm is that, okay, HI, let's say HI is the hypergraph we get at step I. Then the Laplacian Li is deterministically determined by HI. So it doesn't depend on whether we sample like previous hyperedges and add it to the sparsifier. Well, okay, we don't care. Li is deterministic function. So sampling of each EI is independent to each other. So which is nice for analysis. And we only maintain sparsifier H tilde I and the Laplacian matrix Li. So okay, so H tilde I could be bigger than n squared, but the working memory is just storing. We need memory for storing Li, which is basically n square space. And okay, H tilde I is an epsilon delta spectral sparsifier of Hi with high probability. And the analysis is basically based on the chaining analysis. Well, okay, to explain it, I need to introduce a lot of things. So let me skip it for here. Yeah, maybe we can talk about it offline or something. Okay, so how can we analyze the expected number of hyperedges? Well, we can analyze it this way. Just consider a potential function phi I, which is log determinant of Li. Li is the Laplacian we constructed after getting ith hyperedge. And the phi 0 is, because of the regularizer, it's bounded from below. Log det eta I is, yeah, it's not negative infinity, it's something. And well, we can show that if you look at like expression of phi I, we can compute and say that potential always increases by pi. Pi is the sampling probability of hyperedge, EI. And okay, so what is the final potential value? It's going to be log det of Lm plus eta I. And yeah, so we can analyze it. And then we can basically say that it's bounded by n times log of W. So expected number of hyperedges is basically sum of PIs. Okay, we have some constant some parameter like log n or epsilon, but if you ignore it, it's basically sum of PIs, and it's it's upper bounded by the sum of potential differences, and then by telescopic argument, and we get phi minus phi 0, which is like n times log of W. Yeah. Okay. So it's good. It's okay. I'm almost on time. So this is what we did in this work. We showed online algorithm with n times log of W hyperedges with n square space. And we know that this is basically tight for graphs, but we are not very sure whether the bound we got for hypergraph is always tight for example, when the hypergraph has like hyperedges of large sizes, then I'm not sure this log W is always needed. So this is, well, it might not be like big open problem, but one open problem. And okay, more interesting question is whether we can reduce the space complexity from n squared to say n times r, where r is the maximal size of a hyperedge. Yeah, we are storing weighted graph, so we need n squared many space. But well, natural idea is to apply sparsifier on the n squared, sparsifier on the like stored weighted graph, but I don't know whether it works. Yeah, for the free dynamic setting. Oh, okay, so this is online, and this only cares about edge insertions, but not in the streaming setting. It is also natural to think about edge deletions. And for the free dynamic setting, NR log M size sketch was recently shown for cut sparsification, and I guess there's a talk about it tomorrow. So day after tomorrow. So yeah, let's look forward to it. So NR times log M is a little bit worse than the bound that we got here, because basically for undirected hypergraphs, unweighted hypergraph, W is compared to M. So this is basically N log M, and this is NR times log M. So this is R times bigger, but well.
That's a bit complexity bound.
Okay, that's been complexity bound. So we can like divide it by log N, or R. Okay. Oh, R times log N. Oh, okay, that's good. So basically, you beat me. Okay. Okay, that's good. Okay, yeah. Okay, this is for cut sparsification. Okay, yeah. So okay, so then new open question arises. So whether the question is whether we can design sketch for spectral sparsifier. Yeah. Okay. Thank you.
question for you?
Yeah, just very basic question to understand the difference between cut sparsifiers and spectral sparsifiers. I guess the first has to work only for 0, 1 vectors, and this one has to work for
Any x,
any 0, any vector.
any vector x, yeah.
Is that the main difference?
Yeah.
Is there any kind of a simple example of a cut sparsifier that's not a spectral sparsifier? The simplest example.
Sparsifier, which is not spectral sparsifier. Okay, well, I guess the very first cut sparsifier designed by Cargill was not spectral sparsifier because, well, I don't have like small example to explain it, but it doesn't care about a spectral quadratic form at all. So I don't think it's spectral sparsifier, but I don't have like small example. So
Can you get rid of the dependence on delta by any chance? I mean, is it possible to get pure old epsilon spectral sparsifiers?
without data
Yeah.
at all?
Yeah. The online.
Well, so basically you don't like the additive error.
Yeah.
Okay. Yeah. Well, for unweighted case, yes, that's what I think I mentioned it here. So here, well, if the graph is like unweighted or uniform hypergraph, we can set delta to be some number specifically, then we get that bound. So in that sense, this yeah.
Any other questions? Okay, if not, let's thank Yuichi and all the team.